So, hello everyone. My name's Raphael. I'm a pen tester at Fenrisk Security. And together with Osama and Guillaume, who I hope are in the room, please raise your hand. I see one. Where's the other one? I see another one. Great. And with the technical help of Benoît Morgan, which you've already seen. Osama and Guillaume are working at Orange Cyberdéfense, and of course Benoît is at Intel. We've worked on the pre-challenge for the THCon 2026, and we'll have a special guest of Fabien for the write-up for this pre-challenge. So I'll start by speaking quickly about what the pre-challenge is. Then we'll have the, I guess, marvelous write-up, and then we'll move on to the prize. So the pre-challenge is a long-form, about 30 days, linear challenge that aims at promoting both the conference, but also the challenges that do it. The idea is that the difficulty is quietly increasing toward the maximum level. And so, as it was my first year of being the challenge lead, after Benoît did it for 3 years, I took a step back and I'm like, okay, what makes a good THC pre-challenge? First, you need to have something that's utterly weird, okay? You need something that starts slow, but then ends up properly insane. And then you need to fail, like a lot. So, with that in mind, I can assure you that we at least got the last point right. And I hope we got the first two also. So this year, the story, which you can find on thcon.party/lore, is the follow-up of last year. And it will be at the CTF also. The idea is that you need to find out who or what attacked Saint-Symphorien de Tenière Dynamics, which is the main weapon and robot factory in THC. It provides combat robots and stuff like that. So it's a pretty important supply chain risk. The test was in 4 chapters. The first one was very easy. The idea is that everyone should be able to do at least step 1. As I said, my mom should be able to complete step 1, which she actually did for the record. And regular humans should not be able to complete step 6, and I think we were good at this point also. So then we moved to web and reverse engineering challenge, which was supposed to be medium, turned out to be a bit hard. Then an exotic MISC challenge, which was even harder, and then an insane steganography challenge, because we usually want to put steganography at the end, else people complain. So, what did people complain about last year? Steganography, no big surprise, and the fact that challenges were too hard at the start. Our fix, we've put really easy challenges at the start. So people complained that the gap between step 2 and step 3 was too high. I guess we are Frenchmen, we complain, that's our thing. So you can look at the beautiful graphs. I'll draw your attention on the one on the left side on the top, which shows a beautiful decaying curve, which is exactly what we wanted, because it means that pretty much everyone was able to do the first challenge, and mostly no one did the last one. So that's actually what we wanted. We can also see that there's a very weird spike of people doing the pre-challenge 1 or 2 days before it. There's even someone who solved the whole pre-challenge in 3 days from the day before yesterday to this morning, 2 p.m. when I did this presentation. So we had 70 participants, which is great, because we had a great dip in 2025 and we're back to the normal values. We have 4 finishers, which I think is the maximum we've ever had. Yeah, that's it. You can pause on the video if you're watching on YouTube to get the full rundown. And we also got very good feedbacks from the finishers for step 3 to 6, so we're very happy about this. Now, for the failing part, because we said that it's important. Testing is doubting, and planning is having a disturbing lack of faith. So we did not test, of course, because this is outside of our working hours, mainly from 11 p.m. to 3 a.m. And we did not plan, because because planning a release is for losers, right? So to quote a highly underrated philosopher who's sitting on my left, switching to prod is 4 commands. You don't need automation for that. Oh, wait, I'm stuck in a meeting. Oops. So we actually launched the pre-challenge something like an hour after the countdown ended. But when in doubt, never admit your mistakes. It was daylight saving time day change in France, or the next day or something. So at least we had an excuse. At least. We also had some communication mismatches because there's both the CTF and the pre-challenge, and in the CTF, the doc images are per team, so that you can blow up your image and not bother the guy next door. But for the pre-challenge, we did not have that, and some challenges were designed actually with the CTF version in mind. So we've got dust, and the thing is, it probably was just a random guy trying to do the challenge and clicking, and anyway, so we patched it. Luckily, it did not come. It did not come back, but we at least had to reboot the instance once in 40 days. I encourage you to keep this detail in your memory, because for the step 3, which is the one that had to be rebooted, here is the summary. You need to use a local file include, you fiddle around, you brute force your PID, you get the path of the binary, you download the binary, you download other things, you reverse it. And at the exact moment that we rebooted the instance, one challenger just downloaded the flag that was in the temporary file, like 1 second out of 40 days. So, I mean, guess I'm not playing Lotto today, so. I will now give the floor to Fab, and please a thunder of applause for the beautiful write-up that I guess we have.
Control. Let's go. Up. Okay, so I will present you my solution of the Prechallenge. First, who am I? I'm Fabien. I'm one of the technical leads of the reverse engineering team in Synactive. And I enjoy breaking challenges for about 20 years now. I don't know if some of you remember the Security Challenge 20 years ago, but it was the first one I did. So the challenge, as Raphael said earlier, there were 6 steps. So the first 2 ones were easy web. Third one, a mix of web and Pwn. 4 and 5 were about Python textual, and the last one was steganography. So for the first steps, we are given a link to the SST Dynamics website. So that's a website. We can browse the site. There's nothing very interesting on the site, but if you look at the source of the page, you can see that there's a link which has been commented for a /secret URL. So, and if you access the secret, you are given this page. So it's a customer management interface, and then you get a first URL, which is in fact the first flag. So yeah, you completed the first step, so it was yeah, really easy. So now we can see that we have an ID in the URL. So what we do some brute force of the ID until we find an interesting user. So the previous one was a customer, and this one has a full access level. But there's a comment which says that to access the administration panel, we have to use a specific browser and from a specific subnet, which will be an internal subnet. So we need this browser, we need this subnet. What we can do is simply spoof the user agent, add an X-forwarded for header, so we can trick the website into thinking we are from the internal subnet. And then we can have access to the control panel and access the second URL. So now the organizer told us that they have found the C2 of the hacker of the website. So they gave us the URL, and they say that we have to access a file in /app/flag, and well, we don't know the exact file name. So this is step 3. We can load the C2, so that's a C2 with 4 different tabs. So the sessions tab, in fact, it's just fake sessions displayed just for the lore. We have a payloads tab where we can upload and download payloads. A builder tab which is also fake, and an encrypt tab for encrypting our payloads. So the first thing we look at is the upload and download feature. So there's an API where you can upload files with the API payload. You can download a file with API payload download. It's quite simple. To upload a file, you just issue a post request to payload with your file name, your content. And then you can download the file using the other API by providing simply a file name. And then you get the content encoded in base 64. So let's try some random things. If we add a / before the file name, we get our file. Okay, that's cool. If we add // before the file name, we also get our file. Okay. But if we simply put a / before the file name, then it's a failure, file not found. So, well, that seems to be a normal behavior with the / and the /, but the / should not return normally our file. So what we can think here is that the / might be filtered. So we think that we might be able to bypass it by using 3 / 1 /, which after filtering will result in a simple // So yeah, we can try to get etc password by adding enough 3 / 1 /. And yeah, we are able to get the password file, so the guess was good. And we are now able to read every file on the server. So what we can do now is build a Python script, so we are able to download any files easily. So we can get the etc password. Then we can query the procfs, so we can know which binary is currently executed on the server. So we can see that it's a binary called API. If we grab the environ and then grep on the pwd environment variable, we have the path, and then we're able to download the full binary, which is in app API. So this is an ELF file. It's 19 megabytes binary. And we can start studying it. So the API binary is in fact a huge web server in Golang. It uses the Gingonic web server. There are API endpoints for all the feature we saw on the website. So for the payloads, you can list, download, upload, delete the payloads. And there's also the API endpoint for the encryption feature. By looking at this feature, we can see that the parameters which are sent to the API are written in a file called tmploader.in, and it waits for a response and then read the tmploader.out file and return it to the user. So next question is, who handles these files? Remember that we can read the proc file system, so we can implement a PS-like by iterating on the PIDs in the proc file system and reading the CMD line file. We will do it around our PID because it will be a bit slow to enumerate all PIDs from 0 to, I don't know. So we can grab our PIDs by reading proc self status and then do some brute force. And we can list some process running on the machine, and we see a binary called app_loader, which looks quite interesting. Oops. So we can grab it with the previous vulnerability. It's another ELF. There are obfuscated strings, so we have to write a small script to be able to deobfuscate all the strings. we can see that it creates FIFOs in TMP loader in and loader out. It reads loader in a loop. The input should be 3 different lines, which are directly returned by the previous binary. And those lines correspond to 3 arguments. First one is algo. It's an integer between 0 and 99, a key in hexadecimal, and a file name, which should correspond to an uploaded payload. Then it forks and enters a state machine. The state machine, I don't know if you can read everything, but state machine starts in state 0. So state 0, it opens the loader.out file. It sets the key size depending on the algo provided, and it checks if the algo integer is lower or equal to 2. And there's the first vulnerability in this check. Next step is step 7. There's an additional check on algo if it's greater than 2. Well, that's weird because it shouldn't be greater. Then step 3, it will decode the key, obfuscate it, and it prepares an array of 3 obfuscated function pointers, and it will pick one of these function pointers using algo as an index. Then it's state 19. It will read the input file. It checks if it starts with a hard-coded value. If it starts with this value, it jumps to state 42. Which will copy the file content in a fixed size stack buffer, which is another vulnerability. And if it doesn't start with this value, it will check in state 5. If the content starts with cat, it will then close stdout, replace it with a pipe, call the encryption function pointer, and write the output in the loader.out. And finally, it will write the encrypted file, etc. So, well, it's a quite complicated state machine. And there's at least 2 vulnerable paths. So as I said, in state 0, the algorithm can be greater than 2 because there's a check, but if the check fails, there's only an error log, but the state machine will continue. There's an additional check on state 7 with this complicated formula, but we can just try different algo values until one will match, and value 5 matches. And then in state 3, as I said, there's an array of 3 function pointers which is created. And so if we provide an index greater than 2, we can read out of bound this array of function pointers and then grab another function pointer. What is interesting is that this array of function pointers is located just before, in the stack, a buffer in which our encryption key is decoded. So we can control what will be read out of bound. And then the function pointers is called in state 5 with the file content as first argument. So yeah, some IDA captures to show you. Variable S is the array of function pointers. Keybuff is where our key will be decoded. And yeah, you can see that the array is built here. Then you select one of the function pointers depending on the algo int which we control. And finally, it is called here with a replaced stdout. So as I said, we can use the index 5. So in a key buffer at index 8, it should contain an obfuscated pointer to a function. So we can choose the system function. We also have to obfuscate the key because in the code there's some obfuscation of the key, but it's something we can invert. Our file should start with cat, so yeah, we can just cat app flag star, and then we need simply the system address to be able to call it. For this, we can simply read the proc PID maps files to grab the address at which the libc is mapped. So yeah, we have the binary PID. We can read the maps file, get the libc address. We can dump the libc and find the system address. Then we upload a payload containing the command, and then we call the vulnerable endpoint and call system with our file content. And finally, we get another URL. And we have completed step 3. So for the next step, we are provided with an SSH access with default username and password THCT, CHCT. So the next two steps are about Python textual. So Python textual is a Python framework to be able to design a UI in a terminal. So when we connect using SSH to the server, we are provided with this, this interface. We have also access to the Python source code of the application. Looking at the source code, we can see that there's one user called admin and a password made of random characters. So it seems that we first have to find an authentication bypass. But first thing, I will do a quick explanation of Python textual. So with textual, your application can have different screens. For example, the screen we saw before is the authentication screen. And when we will be authenticated, we will have another screen. Each screen has a layout with different widgets. And you can define some actions at different levels. So at the level application, at the app level, at the screen level, or the widget level. If you define an action at the app level, you can call it from any screen or any widget. If it's defined at the screen level, then actions can only be called from this screen or all the widget it contains. And an action defined in a widget can only be called in the context of this widget. So let's find an authentication bypass. Reading the code, we can see that there's an interesting behavior. If we have a failed login, we have a message, access denied for operator, and our login with some bold tags. So yeah, if we type admin with no password, it says access denied for operator admin, and admin is in bold. So what happens if we try to inject some other tags? Yeah, our login is displayed with italic. So yeah, that's cool. We have markup injections, but what can we inject which can be interesting? If we read the Python textual doc, we can see that we are able to inject some kind of links which can be clicked to trigger some actions. So yeah, you have to inject this kind of tags, and then you can call any action. So it means that we are able to trigger the login action simply by injecting this kind of tags. So let's do it. We use this as the username, and when we click authenticate, we can see that we have access denied for operator X underlined, and if we click on X, we are logged in and we have bypassed the authentication. And then we have a new URL, which means we have completed step 4. Here, if we read the secret.md file, it tells us that we have to be able to read a file on the server, which is called /transmission.md. I don't know if we can read it, which is in the root of the file system. So step 5, what happens now? It seems that we might have a new injection because, as you can see in the top of the new screen, our login is inserted again. The login we have provided as argument to the login action. So we might be able to do a new injection. We have to read the transmission.md file, but in the view, the directory tree is initialized on the home directory of the user. So we can only have access to the files in the home directory. There's an open file action, which is registered in the application, but it's defined only in the visible directory tree widget. So what can we do? We can try to make a double injection. So we can inject a new click tag in our fake login, but when we will click on it, the action will be triggered in the header widget. But the open file action is not defined in this widget, but in the other one. One thing to know is that the 3 possible namespaces for calling an action are app for the application, screen for a specific screen, and focused. Focused will be used to target the widget which has the focus. But we can give the focus to the widget we want, but if we click the link in the other widget, the widget will grab the focus before the action is executed. So we are not able to directly use it to trigger the action. The solution is to make a triple injection. We can use a built-in action. There are several built-in actions in the framework, which is called app notify, which will spawn a notification with the custom content. So if we inject a new click inside this notification, the focus won't be changed when the action is clicked, because you can't have the focus on a notification. So the plan is to do a triple injection. We click in the header, it will spawn the notification. We click in the visible directory tree to make it focused, and then we click in the notification to trigger the action to open the file transmission.md. So let's do it. We inject this triple injection in the login. So yeah, access denied. We click, then we are logged in, and as we can see, we have a new click here, which has been injected in the header. If we click it, we have the notification here. We can now click on this widget to make it focus, and then click the notification, and hop, we have opened the file transmission.md, and we have a new URL, which means we have completed step 5. And here we are, step 6, steganography. So yeah, for this step, it was not my favorite one. We are provided with several files, two wave, a .crypt file, and a readme.md. The readme contains an OpenSSL command line to be able to decrypt the encrypted file. About the two audio wave files, they are different in size, duration, content. When you listen to it, it's classical music with some weird glitches when listening. So yeah, know what? Usually for this kind of steganography audio challenges, the Audacity tool well, is a good choice. So let's try to open the first file. First thing I saw is that during the first second, there's some noise, some random noise. Well, I spent really too much time on it trying to find something inside the node, but it's a dead end. So, well, let's have a look to the spectrogram. Usually, it's used to hide the data in these kind of challenges. So, looking at the spectrogram, we can see that there's some weird pattern in the low frequencies, and we can try to decode this pattern as a sequence of bits. So, well, the clear squares are 1, and the other one are zeros. We tried this kind of decoding. Then we create a script to brute force some parameters. So, well, we can brute force the start, the encoding, 7 or 8 bits, the bits values, which is a 1, which is a 0. And finally, we can have a string saying you got the ID. So it seems we got the ID. So now let's have a look at the second audio file. In the spectrogram view, that's not exactly the same, but we can see that there seems to be something weird in the beginning of the file. So, well, I won't describe everything I tried because I spent some time. But by playing with a few settings, for example, increasing the window size of the spectrogram and zooming on the low frequencies, finally we can find something strange, which looks like a new encoding. So same idea as before, we can decode it as 0 and 1s. So there are 7 lines, which might mean that it's a 7 bits encoding, and 24 columns, so maybe 24 ASCII characters. So yeah, we try to decode it as 0 and 1s, and finally we have this output decrypt with path_the_arm. So we can use this as a key in the OpenSSL command, and we have an output file which is a tar archive compressed. So yeah, that's nearly the end. In the archive, there's a transmission for the AI, the hacker, Madam Maxima, saying that THCT will be destroyed, and a video file. So yeah, I was hoping that it was not another steganography step. Hopefully not. You just have to read the EXIF data, and then you find the final URL, which tell you that you have completed the challenge. So yeah, thanks to all the organizers. It was a fun one, and well, if you have any question.
Congratulations. Osama, Guillaume, can you please come on the stage? I don't know if anyone has any questions. Are you still alive? Sure, great. So for the podium, so on the first golden medal was Swap.js, who will perhaps eventually do a write-up of his version of solving the challenge, because some steps were actually solvable in a myriad of ways, including, for instance, the terminal one. Then we have Fab in the second place. In third place, we have Carambol, which I believe is not here today. And in the runner-ups, we have gbell27, then some characters that bugged the LaTeX compilation, who flagged this morning at 2 a.m. And who could not come, but he did flag right before the presentation. So we have 3 prizes. If you can come over here. We have 3 prizes. I guess you can pick and choose whichever you want.